Alright folks, so I'm kind of back here. I've cleaned up the diagram, did a little bit of work here on the sides. So again, in the previous video I showed about how the alpha here that we are using in these Newton's second law equations here, and here, we calculated to be 32.5 degrees. Alright, now I wrote out an expression for the acceleration of this system, since we're going to be using Newton's second law in radial and theta coordinates, or cylindrical coordinates. Alright, so now here's how r is calculated. R is equal to a over theta, where a is equal to 0.2. That makes r dot equal to this expression, just hitting that with one time derivative. And then r double dot equal to this expression, hitting that with another time derivative, keeping in mind that we have to quotient rule this. So derivative of the top times the bottom minus the derivative of this times this over the bottom squared. So working these values out, let's see what we get here. I get for r dot, looks like this comes out to be about minus 0.4 meter per second. And then r double dot, putting in the numbers here, comes out to be, it's looking like about positive 2.42 meter per second squared. So we have these values now, so now we can calculate the a sub r and the a sub thetas. So the a sub r, right, that's this animal right here. Putting in these numbers, r double dot minus r theta dot squared is looking like, I think that's going to come out to negative 7.7, I'm sorry, negative 0.77 meter per second squared. And a sub theta works out to, if I did this right, again, a sub theta is here, r double dot plus 2r dot theta dot, and I get, let's see, I think when I work this out, negative 3.8 meter per second squared. So again, we got negative 0.77 and negative 3.8 meter per second squared. So now it's time to go back to our Newton's second law equations, and I'm going to take a minute, clean this up, rewrite those Newton's second law equations, putting in all the numbers. So if you just kind of hang loose, I'm going to pause this a moment. Okay, I wrote out the first Newton's second law equation we had, n cosine alpha equals m a sub r. Little note here, looks like I forgot to put the subscript on this, but this n is coming from here in the free body. See the n cosine alpha, that's n1. So I'm going to go back and put a little 1 on there. So this equation is n1 cosine of 32.5 equals ma. Putting in the values, it looks like I get a normal of about minus 0.45 newtons. Then the second equation we have, right, that's this animal, so we're going to have n2 minus 0.45 newtons times the sine of 32.5 degrees is equal to the mass, which I think was 0.5 kilograms, times a sub theta. And we calculated a sub theta earlier to be negative 3.8 meter per second squared. I guess if I'm leaving units off anywhere, I'll leave them off everywhere. So now, since we have n1, we can calculate n2. I'm going to pause this for a moment while I work on that. Okay, looks like I got around minus 1.7 newtons. So hopefully this is hopefully this works out good for you. Hopefully this has cleared things up. So, the key to this stuff, draw a good free body, choose a set of coordinates. I strongly recommend using straight edges to draw your vectors, draw the coordinates, because these problems are kind of complex in this region, and it takes really good pictures to sort that stuff out. That's why I made the video using this drawing pad, because the pad allows me to use a nice straight edge feature to draw these vectors, and it helps me sort that stuff out. You'll notice when I sketch these on the board, it becomes very easy to get lost in which angles are which here. But draw really good photos or really good pictures, use straight edges, and I think that'll help. So please post if you have any questions. Right?